In this lecture, I will discuss about parallel in serial out shift register. In the previous lecture, we have discussed about serial in parallel out shift register and parallel in parallel out shift register. Now we will see how to design parallel in serial out shift register. Now if we observe the name, that is parallel in serial out, so here we have to perform two operations. That is, first we have to load the data parallelly, then we have to take the data serially out. Then how to take the serially out? So first we have to shift the data one by one. So that means two operations: loading the data, then shifting the data, right? Now first we will see the block diagram of parallel in serial out shift register, then later we will see the internal circuit diagram and operation. So if I see, this is the 4-bit parallel in serial out shift register block diagram. So here we are loading the data parallelly, that is 4 inputs, and we are shifting the data towards the right side to take the serial data out. And we are using the here positive edge triggered clock, right? If there is no bubble, it is a positive edge triggered clock. Now here, so I said two operations we have to perform, but we cannot perform simultaneously. So first we have to perform one operation at a time. That is, first we have to load the data parallelly, then we have to shift the data towards right. Then whenever there are two operations, we need some controlling element to control those operations. So that's why in this parallel in serial out shift registers, we'll have one extra input that is called control input. So this control input will tell when to load, when to shift the data. So that's why the name will have shift or load bar. So load bar means it is an active low, shift means it is active high. That is very simple. How the operation will takes place is shift or load bar is equal to 0. So 0 means load bar will become 1. That means the loading will happen. So parallel data will be loaded into the register when shift or load bar is equal to 0. It's like a control input, or we can say select line. When S is equal to 0, it will load the data. So when shift or load bar is equal to 1, that is 1 means shift is equal to 1, so it will shift the data. So here the data will be shifted towards right side or left side. If you see, it is towards right side, so towards right side, right? So these two operations will take place one at a time. So that depends on this control input. Now if you remember which type of combination circuit will perform this operation, so we are having two operations, one is load, one is shift, but one at a time. So which combination circuit will perform that operation? So that also first we will see. So it is nothing but multiplexer, right? So I'm having two operations, one is load and one is shift, but I need one operation at a time. So we have to use multiplexer. That is, here we are having only two, so 2 by 1 mux, and this is a select line. So depending on the select line, so it will perform the operation. So this select line I'm using as shift or load bar, and this is the output. Now very simple. So select line is equal to 0. So here we have to give the number, that is 0 and 1. So when S is equal to 0, it will select the load operation. So when S is equal to 0, or we can say this is shift or load bar is equal to 0. So what is the output? So generally it will perform the loading operation. So it will perform the loading operation. Then when S is equal to 1, select line is equal to 1, or we can say shift or load bar is equal to 1, so output, or we can say the circuit will perform shifting operation, right? So very simple. So we have to use this external circuit, that is combination circuit or combinational gates, right? So to perform these two operations one at a time. Then how to implement this 2 by 1 mux using gates, that also we have to see. And in the logic diagram, either we can use this 2 by 1 mux directly the block diagram, or we can use this AND gates, OR gates also. So how to implement? if I write the expression for output, so this is nothing but S bar. When S is equal to 0, we are performing the loading operation. So S bar into load plus S into shift. Yes or no? So we are having two operations. One, when S is equal to 0, it will perform the loading. When S is equal to 1, it will perform the shift. Now here see, this is AND operation, this is also AND operation, then again OR operation. So 2 AND gates, 1 OR gate. So this is the output. So one input of this AND gates will be the loading, or we can say the input data, and one more input is coming from this select line. So this will go to this AND gate, and this S will go to this AND gate. What is the other operation? This is shifting operation. So this is the implementation of 2x1 mux using gates, AND gates and OR gate. Right? Now we will see the logic diagram of this 4-bit parallel in serial out shift register. So this is the logic diagram of 4-bit parallel in serial out shift register. So 4-bit means we have to use 4 flip-flops, and all flip-flops are clocked simultaneously with the positive edge triggered clock. Right? And the first flip-flop generally will give MSB output, and the last bit or last flip-flop will give the LSB output. So when I want to store, suppose 1 0 1 0, so 1 will be stored here, 0 will be stored here, 1 will be stored here, 0 will be stored here. Then we can take the data serially out from the last flip-flop. Now here we need to perform two operations. So one is, first we have to load the data parallelly, then we have to shift the data serially. Now that also we'll see. Now so we have to implement these operations, two operations using multiplexer. So that multiplexer will be implemented by AND gates. So here I am using 3 multiplexers. First, for a first flip-flop it is not required. So it is only storing the data, right? So if I want to shift, so Q3 will be shifted to this Q2, Q2 will be shifted to Q1, Q1 will be shifted to Q0. So here we don't require any multiplexer here. Now we will see the how to connect these inputs. Now shift or load bar here. So whenever I am using the NOT gate, so it will give S bar. See the select line S bar. This is the S. Now when S bar or when S is equal to 0, I have to load the data. So that is when S is equal to 0, this will become 1. So this 1 will goes to which gate? So to load the data. See, this I2 is connected to second gate, I1 is connected to fourth gate, I0 is connected to sixth gate. So this S bar should be connected this second gate, fourth gate and sixth gate, right? Then when S is equal to 0, this I2 into, see S is equal to 0 means what happens to after the NOT gate? 1. So 1 into I2, so that will goes to here. Then 1 into I1, that will be goes here. Then 1 into I0, that will be goes here, right? Now depending on the output of this 1, 3, 5 gates, so we'll get the output of this OR gate. Now when S is equal to 1, so we have to perform the shifting. Now how to perform the shifting? This Q3 will be goes to Q2. How? So depending on this select line. So if I connect this Q3 output to the AND gate of the, so if I connect this Q3 output, the input of the first AND gate, similarly Q2 output input of this third AND gate, and the fifth AND gate input is Q1, right? Now this Q3 is here. Then depending on the select line, so when S is equal to 1, so this should be selected. So that's why this shift or load bar should be connected to the input of the first AND gate, third AND gate and fifth AND gate. So here second input of this AND gates will come from the select line. Now we will see the operation, how it is performing the loading and how it is shifting the data. Now that we will see by using the table. Now here the operation will be performed in this table. So here clock, so we have to apply the positive edge triggered clock 1 2 3 4 and so on. This is the control input which will control the operation, and this is the data. So we are entering which data we need to store or shift. So this is I3, I2, I1, I0. This is the state of the register, and we can take the output serially. Now suppose if I want to store the data 1100, right? So in this, what is the LSB? The last bit is LSB or right side, and this is the MSB, leftmost bit, right? Now first, so anyway, this is we are applying the parallelly, so we can directly apply this 1100 to the input of this I3, I2, I1, I0. So if I apply that one, sorry, here 1100. Now we have to give the control input. So we are loading the input. So the shift or load bar should be 0. So when shift or load bar is equal to 0 and we apply the data as 1100 to the input of I3, I2, I1, I0, then what will happen? So that we will see in the circuit. So first, what is shift or load? It is 0. If this is 0, where this 0 is going? So here, here and here, and 0 bar will be going where? So this is the 1. So this is the 0 means output of the NOT gate will be 1. So that 1 will be going here, here and here. And what is the input we applied? Here 1, 1, 0, 0. Now we'll see what will happen. So this I3 is coming to the input of this D3 flip-flop. Then if I see, this is the 0. So 0 into anything. So 0 into Q3 will be 0. So here I will get 0. So this is the 1 and this is 1. So 1 into 1, the output of the AND gate will be 1. So what will be the output of this OR gate? It will be 1. Right? See, 1, whatever we applied, I2 is equal to 1, that is going to the input of D2. Similarly here, 0 into Q2 will be 0. Then 0 into 1, 0. So what is the output of this OR gate? Will be 0. Similarly, so here 0 into anything will be 0. Here 1 into 0, 0. So what is the output of the OR gate? 0. So here, the moment we apply shift or load bar is equal to 0, whatever the data we applied at the input of this I3, I2, I1, I0, that will be transferred to the input of the all the flip-flops. Now if we apply the clock, what will happen? This 1 will be transferred here. So this 1 will be transferred here. This 1 will be transferred here. This 0 will be transferred here. This 0 will be transferred here. So what is just happened? We loaded the data parallelly depending on this control input. So when shift or load bar is equal to 0, so we are loading the data parallelly. So that we will see here. So 1100 and shift or load bar is equal to 0. So we applied the clock, that is a positive edge. That's why the arrow is upward. So the moment we apply the clock, this will be simply loaded in this register. So 1100. So loading is over. Next, what is the next step? We have to shift the data serially out. Now before that, so I will write down what is just happened in words. So here I am writing the first operation. When shift or load bar is equal to 0, so which gates are enable, which gates are disable? These are the AND gates. So when shift or load bar is equal to 0, the second, 4 and 6th gates are enabled, because one input of these AND gates are 1. So 1 into I2 will be transferred here, 1 into I1 will be transferred here, 1 into I0 will be transferred here. So 2, 4, 6 AND gates are enabled. Now what happened to the other gates? 1, 3, 5. So one input of this AND gates are 0. So 0 into anything will be 0. So those are will be disabled. So 1, 3, 5 AND gates are disabled. Right? So very simple. Next, now what is the next operation? Shift or load bar is equal to 1. So what will happen? Opposite. So here 2, 4, 6 AND gates are disabled, and 1, 3, 5 AND gates will be enabled. That also we'll see. Right? So when our 1, 3, 5 gates will be enabled, then shifting will be takes place. That we will see. Now we'll see here. Now if I see what is the current state of this register 1, 1, 0, 0. Now if you see the circuit diagram where we are taking the serial out data from the last flip-flop. So this 0 is already available. So take it out. So this 0 is already available. So just take it out. So we can read this 0 at any time. So 0 is available already. now we have to shift these 3 bits to serially out. Now that we will see. So whenever we want to shift, what happens to this control input? Shift or load bar should be 1. So whenever this is 1, what will happen? We will see in this circuit. So I'm using different color now. So here shift or load bar is 1. If this is 1, what happens to output of this NOT gate? Will be 0. So those zeros is going here, here and here. So 0 is coming to this second, 4 and 6. So that's why 2, 4, 6 AND gates are disabled. So there is no meaning of this 2, 4, 6 gates. Now 1 is coming where? In this, the downward 1 and 1. So 1, 3, 5 AND gates will be enabled. So this is 1. So whatever Q3 is there, so Q3 into 1, here I will get Q3. So here I will get Q3, and here Q2 into 1, so I will get here Q2, and here Q1 into 1, so here I will get Q1. Now see what happened just. So shift is equal to 1 means this Q3 is going to the input of this D2. Yes or no? See, this is Q3. So what happens here? This is disabled means this is 0. This is also 0. This is also 0. So Q3 plus 0. So what I will get? Here Q3. Here I will get Q2. Here I will get Q1. Now what just happened? So this 1 is going to the input of this D2 flip-flop. This 1 is going to the input of the D1 flip-flop. And here I did a mistake, that is I have written 1 but it was 0. So please make correction. So it is 0, okay, because we are loading 1 1 0 0. Now what will happen? This 0 will be transferred to the input of this D0 flip-flop. Now if we apply the clock, what will happen? So this 1 will be transferred here, this 1 will be transferred here, this 0 will be transferred to the output of the last flip-flop, something like this. Now see, this is a 1. So this 1, if I apply the clock, this 1 will be transferred here, this 1 will be transferred here, this 0 will be transferred here. But what happens to the Q3? Now if we see the circuit diagram again, I3 is given as 1, so that will be fixed always. So the D3 input is 1, so what happens to the Q3? It will be still 1 only. So because actually we don't require that Q3, but if you ask what happened to this Q3, this will be still 1 only, because we are applying the clock for all the flip-flops. All the flip-flops will work simultaneously. Whatever the input is available at the input of this D flip-flop, that will be transferred to the output. So here shifting is towards right. Now see, the moment it is there, that is Q0 output, so it is available for reading, so you can take it as out 0 0. This is the after second clock, right? So here we are not applying any, so this will be fixed, right? What is 1 1 0 0, right? Next, when we apply third clock, the shift or load bar still high only, because we are doing the shifting. Here also 1 1 0 0, here also 1 1 0 0. Now what will happen? If you see, the present state of this register is now 1 1 1 0. Now what will happen? Again this Q3 is going to the input of this D2, this Q2 is going to the input of this D1, then Q1 is going to the input of this D0. So if I apply the clock, what will happen? Again it will be shifted. So still this is 1 and this is 1 only. So here this 1 will be shifted here, this 1 will be shifted here, right? Now again this is available, so take it out. Again same operation will perform. So 1 1 1, so this will be shifted here. Again it is available for reading, so take it out. So this is the serial out. See how many clock pulses required to perform the total operation. For loading I required 1 clock, and for shifting I required 3 clocks. So total 4 clock pulses required to complete the operation. So in this operation we are having loading as well as shifting, right? So 1 clock is enough to load the data. Then to serial out, already 1 0 is available. So to get these 3 bits we have to apply 3 clock pulses more. So total 4 clock pulses required to complete the operation, that is loading, and shifting, right? If you observe in the previous lecture, we discussed about the serial in parallel out shift register. There also we required only 4 clock pulses. So this is the operation of this 4-bit parallel in serial out shift register, and this is the logic diagram. If you are having any doubt, please post a comment, right? And I will show you in another way the circuit diagram, so using the multiplexers. So this is the in other way we can draw. So not only like this using gates, we can draw like this also. So here we are using 3 2x1 muxes and one select line. See here, so this select line is given to the shift or load bar. When s is equal to 0, this I2 will be transferred to D2, I1 will be transferred to D1, I0 will be transferred to D0. Anyway, I3 is given to the D3 only. Now the moment we apply the clock, so this I3 will be transferred to the output of this first flip flop, I2 will be transferred to the second flip flop, I1 will be transferred to here, and I0 will be here. So that is loading is done. Next, when a shift or load bar is equal to 1, so it will select this one. So what is 1? 1 is coming from the Q3, right? So here I will get Q3, here I will get Q2, here I will get Q1. So when the clock is applied, the shifting will be done one by one, right? So this is the logic diagram using multiplexers. I mean multiplexer block diagrams. Now we'll see what is the application of this parallel in serial out shift register. Now if I see the block diagram, so what is just happening is, so we are entering the data parallelly and we are taking the data serially. So serial data here will get parallel data, right? So if it is a 4-bit shift register, something like this, this is the clock and this is the control input, shift or load bar. So what is happening here is, we are converting the parallel data to the serial data. So parallel to serial conversions. So whenever we require a converter which is converting from parallel data to the serial data, so we will use this parallel in serial out shift register. So generally where we use this type of circuit is, so again the modems, telephone modems, so which is connect modems. So suppose there is a computer, so this computer will generate data parallelly, so it will generate parallel data, but there is a telephone wire which will accept only serial data, something like this 1011 and so on. So we need a device which will convert this parallel data to serial data. So here I have to use parallel in serial out shift register, right? So remember, telephone modems generally we use parallel in serial out shift register. And remember, all the register whatever we discussed, the microprocessors, if you see, always microprocessors, right? So we have to use this register. When you use this register, so we can shift the data right side or left side, we can rotate also. So the main application of this registers or any shift register will be used in microprocessor, that is 8085, 8086. When you write a command, rotate right or rotate left, right, or shift right, shift right, so this register will perform all the operations, right? The main applications of this register we can tell is easily used in microprocessors like 8085 and 8086, right? So this is about the parallel in serial out shift register. If you are having any doubt, please post a comment. In the next lecture we will discuss the bidirectional shift register. So it will shift either left side or right side. The same circuit will perform the both shifting, right, but one at a time, right?